Welcome, VEST scholars, to the Module 7 video. In this video, we're going to learn about ecosystem change and the carbon cycle in more detail. And this is going to be more than just climate change. It's going to be looking at a lot of different changes in the ecosystem and the goods and services it provides that are vital to human welfare. Goods being, of course, things that allow us to live, and services being things that the ecosystem provides to make it possible for us to be, like flood control and so forth. Make it possible for us to be successful here. This is an example. This image in behind here is an example of an anthropogenically caused algal bloom. This is a Landsat 8 image taken by the Landsat 8 OLI imager, and you're looking at an algal bloom in Lake Erie, off of the coast of South Bass Island is down here, Middle Bass, North Bass, Kelly's Island, and then Paley Island, and all the way up into Canada, primarily as a result of agricultural runoff, especially phosphorus in this case. And this was a really big deal the last couple summers in Lake Erie. And this is a typical summer thing, but it's, again, not normal. Ecosystem change, what we call eutrophication in this case. Well, the lake wasn't eutrophic, but when you have these big algae blooms, of course, it can lead to eutrophic conditions and eventually anoxia from that because of the decomposition of bacteria. So another example, here's a place in the tropical rainforest in the Amazon. Here's a before image and then a secondary image. So again, before image and a secondary image. And there's two things going on here, of course. There's deforestation, and along with this deforestation, you see it has a pattern to it. We can call that habitat fragmentation. And of course, one of the results of habitat fragmentation is that some organisms, that would normally be able to traverse the forest in places like this region over here, for instance, maybe can no longer do that, jumping over this non-forested land. And that can have evolutionary consequences, but it certainly has biodiversity loss consequences. And this is all human. This is all human development. This is the kind of thing we're looking at today. So we're going to take a brief break. We're going to look at weather. So here's an example of drought. So this is in Southern California, Lake Cachuma, and this is what it looked like beforehand in October of 2013, and then just a few years later in 2016, because of the protracted drought in California. Now, this is a great website that NASA maintains called Images of Change. We'll look at a couple of other ones. Here's an example of declining ice thickness. I'll give it a moment to load. And you can see this is from 1984 to 2016. So we look at the entire 1984 image. This is a reconstructed image of ice. You can read about this is from NASA's Earth Observatory. And you can look at the change by using the slider. And you can see that over time, the North Polar ice has certainly thinned out and is not nearly as large an extent as it once was. Now we can look at some other ones here. Here's a calving glacier. As glaciers melt, they calve. They break off small chunks, and of course that's part of glacial retreat. So we're looking at the area in this red circle in this case. So this is 2015 to 2016. And this is, of course, the result of global warming directly. As the Earth warms, the glaciers melt. And calving, that's a really big calved chunk of glacier there. We can choose one more here just to get another example. Here's a good one. It's a little bit different in that this is direct human change. So this is looking at coal mines in Wyoming, Powder River Basin specifically, subbituminous coal mines. And this is what the landscape looked like in 1984. And then as you move into 2016, these are the open pit mines that have been excavated since over the course of that 22-year period. So quite a bit of change here. Now, another way of looking at change is to look at sea level rise. Again, this is a direct consequence of global warming. Sea level is rising for two reasons. One, the primary reason is thermal expansion of the seawater. As it warms, the water actually expands thermally, but also the melting of ice and so forth, and changes in the hydrologic cycle as a result of that. This is NOAA maintains this site, and I focus in specifically here at Hampton, but also Wallops Island. So I'm going to focus in on Wallops Island specifically because that's, of course, got a NASA center located on it. So if we do that, we can pull this little convenient slider over and watch how Wallops Island disappears under 6 feet of sea level rise. And that's pretty significant. We can also use this map to look at the vulnerability. And so this is a way of looking at a direct result of the economic ramifications of climate change. So these are areas in red, especially, that have high social vulnerability as a result of, in the current scheme of things. As sea level rises, of course, a lot of these areas become inundated. Now, if we go down to the Hampton area, scroll on down here, Hampton is a place that is often discussed as one where sea level rise is particularly poignant. And if you look very carefully here, I'm going to zoom in a bit. For those of you who go to the Summer Academy, you'll be going to Newport News, and well, actually, you'll be going to NASA Langley. You'll spend some of your time in Newport News as well. But here is, of course, what happens to sea level rise in the Hampton Newport News area. It's pretty significant indeed. So a lot of the salt marshes that are currently there will no longer be there, and this, of course, is understood to be potentially be able to happen by the year 2100 or slightly thereafter because of global warming. Now, what's going on with that? This is the Mauna Loa Observatory, and we're looking at data from 2013 to 2018, but we could extrapolate it back much further than this. We're looking at the concentration of CO2 in the atmosphere. So if we go back to the carbon cycle, here's the IPCC version of the carbon cycle. We have sources of carbon and we have sinks into which carbon moves. Sources include things, of course, that are places where we can pull carbon out of storage, and sinks are places where we can store it. So in the case of this diagram, of course, you're seeing a lot of exchange between carbon sources and sinks occurring. And so fossil fuels, of course, are an example. Here in the black, we have the total amount of carbon in gigatons of carbon per year. In this case, that's the flux rates, but we're dealing with big numbers here. So 3.7 petagrams of carbon, or minus 244, of course. Minus 244 is what we're pulling out annually, and so forth. And so these exchanges are very significant. And where does that carbon go? Well, it can only go one place. And of course, we're combusting it, so it goes into the atmosphere. And as it goes to the atmosphere, of course, it gets absorbed into the oceans and it goes into the troposphere. Here we're measuring it in Mauna Loa at the observatory there, and this is mean CO2. We have CO2 monitoring stations all over the globe. Here's another one, and I've got it focused on methane right now. It's another aspect of the carbon cycle, because of course methane is CH4, so there's carbon involved there. And here's an example of methane data, and you can see it is also rising. And this is from 1988 to 2016. The methane concentrations are a little bit different. They're a little higher in terms of the number, but nevertheless, the trend is what's important here. Okay, so the carbon cycle, of course, is one of the main foci of some of your work coming up in this module. And going back to this concept of sources and sinks, the two major sources of carbon that humans use come in the form of fossil fuels or in deforestation or land use. It's also known as land use, but typically deforestation. So you cut down forests to produce agricultural land. The two major sinks are generally ocean uptake and land uptake. Those are the best examples of the fast carbon cycle at work. The fossil fuels is part of the slow carbon cycle. Um, so really, when you're pulling carbon out of the fossil fuels, you're pulling it out of a place where it's been stored for millions of years and would take millions of years to get back into that storage. Nevertheless, this is a neat little applet that allows you to control the carbon cycle and run some scenarios. So if I go look at fossil fuels, I can see a direct relationship on what's going to happen with the projected um, atmospheric CO2 levels. Remember, temperature is directly related to CO2 levels. So if my CO2 levels go up, my temperature is also going up. But let's say we can go with the worst case scenario, which is business as usual, and we run the projection, and we watch the projection run over here. Now we haven't adjusted any sinks. We haven't adjusted anything. This is just the default projection. And you can see what happens. We have the we end up with with a concentration of around 857 parts per million. What happens though if we significantly decrease fossil fuel usage, starting in about 2040 down to very low amounts, and then run that projection? We'll get a different result here, and you can see you can compare the two. Actually, appears to be a very unusual projection in terms of. Um, I think the people who made this probably wouldn't have considered this a realistic projection. Nevertheless, um, that is, of course, this is what we call a model. So models are, of course, uh, approximations of reality that allow us to make predictions and have discussions about things we can do to test ideas and to when we want to look for predictions. Of course, we can change land use and ocean uptake and land uptake, but this is just a way of explaining to you, showing you the way things can work now within the carbon cycle and what we might have some control over. Now, this is the C-ROAD simulation put out by Climate Interactive, and what this attempts to do is model climate change based on, or climate change scenarios based on current data and what different groups of countries might do to help with this problem. So let's say the U.S. were to commit to reaching its peak emissions year in say 2010. Well, 2010 is already behind us. Let's just say 20. Let's keep it at 2020. And let's say we begin reducing emissions in 2021, and we do that at an annual reduction rate of 5%. And we prevent deforestation. We do a 20% prevention of deforestation, and we promote afforestation by 10%, or the growth of forests. But what does that do for? Um, what does that do? Well, we can see what happened in the scenario. It actually seems to help a little bit, but that's just the U.S. We don't have anybody else helping. Let's say the EU joined us. They're generally ahead of us when it comes to these predictions, but let's just say they joined us here and made some commitments on their own, and we'll just make their commitments the same as ours. What happens? Ooh, we're going to start to see some of the lines here change. Change this to 20%, and then we'll change this to 10%. Again, we're preventing forest deforestation and also planting forest. And you can see, we've now brought it down to 814 by the year parts per million in the atmosphere by 2100. Now, how about there's other developed nations, of course, and then China, India, and then other developing. Well, what happens if China hits its peak emission year in the year 2020? There's a significant change. Did you see that blue line up here change? Watch that blue line again as I do this. I'm going to hit 2021 for the beginning of reductions. We have to tell how much China is going to reduce. Let's say China reduces also by 5%. That's a significant change. Now we're making big progress because why? China is one of the biggest emitters in the world. It is the biggest single emitter in the world now, surpassed the US several years ago. So now we're at 692 parts per million by the year 2100. It's still high. We're still looking at an overall 3.5 degrees Celsius increase. Now, if India were to do the same thing and adjust its projections as well, we'll change this by 5% again. It takes a little while to go through it because it's got to do the math. We're not even dealing with forest right now. Here we are at 634, 3.1 degrees. Now you can see how difficult this is going to be to counteract. So it's kind of a big deal. This temperature thing is significant. If we look at change in temperature anomaly over the last little over 100 years, and this is a great little simulation of that. NASA's GISS temp scenario, looking at temperature anomalies over a period of time from 1951 to 1980, and comparing the spread from 1880s to the modern day. And you can see, starting in the 1880s, of course, the temperatures started out much cooler, and as we move into the 21st century, the anomalies are much warmer. And this is reality. This, of course, should ring a bell for you when you look at when you looked at the CO2 curve and you saw it constantly going up or consistently going upward. You can also see the temperature anomalies globally doing the same thing. So these are some significant things we're dealing with. When it comes to ecosystem change, there's a lot of things going on that we have to be mindful of. Forest change, biodiversity change. We'll get to that. You'll get to that in your final project. Temperature change, sea level change, marine life change. These are all important things because the reality is, of course, that if we can't survive here any longer, if we destroy our environment, the environment won't be able to provide the goods and services that are necessary to make our life possible. These are things to think about. So as you work through Module 7, and enjoy